quality prediction results include and of course indicate the following. Now you can see the greenness here. You see this greenness now, and the percentage shows that the product has high quality. All right, now the next important thing to that is the yellow. If they are yellow, like you can see in this in the top part, especially where the injection locations are, you can see that there are some yellow parts. So the yellowness indicates that there are quality issues associated with that particular part, that area. Okay, so having completed the injection pressure elaboration and thesis, the next important thing that we want to handle here is the frozen layer percentage at end of fill. All right, so now let's look at the outcome of the results. Okay, I mean, let's just test run the fill analysis and see what is going on. You can see that the fill is going on upwards from the bottom of this object. Okay, and it's going up from a very low percentage to at least 26.30 in percentage. Understanding Autodesk Moldflow Injection Advisor 2024 molding results. This is a special case study for plastic paper basket, a presentation by Hands-On Software Academy. Now, these are the brief table of contents that we'll be covering. Firstly, we have fill time and the plastic flow results. We're going to be seeing more about that. Then the confidence of fill, the quality prediction, pressure drop, temperature at flow front, average temperature, time to reach ejection, air traps, weld lines, ejection pressure, frozen layer at end of fill, as well as grow from. So let's begin by starting up Moldflow Advisor 2024. So having started, we're going to simply create a new project. you can as well just double click this, or you right click and click on new project. If you right click, or you could come over here and get the new projects. Then you can see a handy help file there. So now we're just going to create a project called Baskets 3D mode. So right in here we're going to import a specific object. You can see there we have parts out mouse, mechanical part, paper baskets. Let's look at paper baskets, and then we choose the solid part objects. Then we'll wait for the preview of what we just imported to be displayed, so we can set some basic parameters. So this is the preview of the paper baskets. Now the units, you can you have the option of millimeters, centimeters, meters, and inches. So I think I will rather go with the meters units. The approximate dimensions is this. You can not make exact adjustments to this. You can just leave that as it is. Now these are the links to the objects, the active summary of it. You can see what we're using is 24 version of the advisor. Alright, so you have the option of checking this box, and you see this object properties, the locations and all that. Then now that we're done with this, you've seen the preview as you can see on the screen. The next thing is to of course attempt to import this waste paper basket into the software itself for meshing and analysis respectively. Okay, so you can see that now. You have also have the option of the advanced options, the automatic cleanup, the check suitability. Alright, so you can do this. When you choose the automatic cleanup, is to fix model defects. Then the the suitability option helps to determine whether it is suitable for 3D or dual domain analysis. I've always told you that, you know, discretely, if you're bringing in thick side or six-sided object model, it's most likely going to go with the 3D model. But if it is thin walled, then it's most likely going to be dual domain. So just put that beside your mind. So here we can click, once we're done satisfied with this, click on next, and of course wait for the processing to be complete. The preliminary processing of the imports, the object imported to the Moldflow Advisor software. Okay, so that has been completed. That process is done. Now look at the advice this is giving. It says the imported model is thick and chunky. It is recommended for 3D analysis. You can see, just like what I told you earlier. Now, analysis type, you have the standard and dual domain, and then you have the advanced, the true 3D. So the true 3D is the advanced analysis used by Autodesk Moldflow Advisor. It is recommended for thick and chunky models. All right, show log, yes, I also recommend that you show log. Is important so that you can monitor the progress of your mesh and analysis results. So having done all this, all we need to click now is finish. You can see the object on the screen. This is the waste paper basket. Ensure you have a 3D scroll mouse for, you know, viewing in a very responsive and interactive manner. Now let's quickly use the orbit to see some of the, you know, parts of this waste paper basket. You can see it has its height and its thickness, and of course this is the bottom. This is how the bottom looks like, and then this is the top. This is the top of the basket. So the next thing we want to do now is we want to ensure that this thing is meshed, and then we analyze it to see the results. All right, so let's look at the mesh. Let's try and mesh this and then see how it looks like. Now, before we do anything further, we need to set the injection locations, and in order to do that, you can actually come to these boundary locations and select this particular menu here, or you can as well just come to this place and then select this particular menu, which is the same function as this at the top here. So what I'm going to do right now is I'm going to put the view and then come to the orbit, so that we can position this thing very well for injection, placement of the injection location. So we click on this. Now, prior to clicking this, you discover that the fill, we cannot do any fill analysis here or preview here because we've not yet set the injection location. So or in order to do the fill, we have to set the injection locations. As I've double clicked on this menu now, you can see the icon has changed. So let me just place 1, 2, 3, 4 and 5 at the center there. So I have as you can see 5 injection locations selected. So right now we are in the progress of doing a mesh and of course eventual analysis of this waste paper basket. Okay, so let's try and make do of this analysis, analyze this object and see what this brings up. And prior to running the analysis, we're now going to make do of this field preview. Alright, so you can see the field preview is taking place now. As you can see in the lower left pane of the software, where this cursor is circling, you have 97% field preview. So the analysis is running now. Now this is the field preview. Let's try and see what it looks like. Alright, so this is what the field preview looks like with injection, with respect to the injection locations for the waste paper basket. You can see coordination is taking place from the injection locations. At the same time, I've actually initiated the analysis and it's running. Usually before you make do of field preview, you definitely have to set injection locations. The mesh is running, as you can see at the bottom left. The mesh usually runs, is obligated to run way before the analysis. Now you can see that the coloration for the field preview is green. If you check this, it goes back to the basic object color, that's the default color that comes with the 3D model object. The mesh is about 95% now, and it's almost wrapping up its meshing process. And the mesh for the advisor, the mesh actually is automated to run before the analysis itself. So the mesh is complete and the analysis is about to commence. Alright, so the analysis has actually commenced, and we're beginning to see the results of this 2D basket object. It's currently on 1% field analysis. Alright, so we can see that the analysis is complete. The basket SDY project. Okay, so let's look at some of these results and what they actually mean, their interpretation. Now, right here we'll be starting with the fill time. The fill time result shows the position of the flow front at regular intervals as the cavity fills. This is very, very important. Very necessary thing to also take note of here is that the characteristics that come alongside with it. Okay, you see that all the regions with the same color are filled simultaneously. The result is dark blue at the start of the injection, and the last areas to fill are red, as you can see from the screen. If the part is a short, okay, I'll be talking about short in the in the next few couple of minutes or so. They said if this part is short, the section did not fill and has no color. But in this situation now, you see that virtually everything has specific colors. Now let's talk about the fill time characteristics. Now, the position of the flow front at regular intervals as the cavity fills. This shows it, alright? Now, what this means is that the position of the flow front, especially from the ejection locations, is particularly taken into context. As you can see, the field takes its operations from those 5 locations that are inserted at the beginning of the project work. Now, I also want to mention here that the contour colors are indicative of the flow of the plastic into the part. That's the contours. Then the regions with the same color are filled simultaneously. Like you can see the blue and then the green and then the red respectively. Now regions with the same color are filled respectively, like what I said. Then usually the dark blue at the start of the injection, and then the areas fill to red. Yes, it's blue at the beginning, and then at the ending it's red. All right, now if the part is short, like I said, I'm going to explain briefly very soon. The unfilled part has no color. That's if there's a defect in the filling. Now we should also understand this fact here, that if flow pattern is balanced, a part with a good, that indicates a part with a good fit. Okay, that's if the flow pattern, as you can see, if the flow pattern is balanced. Okay, that means the part, that's, for instance, now in this case study we are looking at the plastic basket, the waste paper basket. It actually means that the part is good and there is a very high confidence of production time. Okay, now also we should also take note that the flow, if the flow takes place like you can see in the animation now at the same time simultaneously, is a very good indication of the end product itself. Then you also should take note of the contours. All right, the contours should be evenly spaced, and they are also indicators of polymer fill flow. This is very, very important. Now another important thing you should take note is that the flow pattern is balanced in a part, okay, with a good fill time result, which means the following: all 4 parts finish at the same time and reach the edges, all right, of the model simultaneously, just like what I said previously. Like in the in this particular diagram now, you can see that each flow part ends with the red contours. The contours are evenly spaced and indicate the speed at which the polymer is flowing. It's very, very important you take note of that. Widely spaced contours indicate rapid flow. Narrow contours indicate the part is filling. All right, now let's talk about what to look out for under this fill time results. One of the first things you need to take note of is that the short. Now, what is a short? This is simply an incomplete filling of a mold part, okay, or rather cavity. You can call it the part or the cavity. It usually results in incomplete, defective products, and has this translucent, attributes in the simulation of the object in question. All right, but in this case you can see that the translucent property is not present. We have an evenness here, so the flow pattern is balanced, and this actually indicates that the part we are dealing with has a very excellent fit for production. All right, that is for short shots. So I've explained that. And another thing you should also understand under the short shot is that during the fill time result, a short shot will appear as translucent. Okay, so you should check the ends of the flow. Okay, the end of the flow part for any translucent areas. Those translucent are like gray areas for models analyzed. Okay, now for models analyzed during a 3D analysis technology, you also should take note of the unfilled cavity, okay, to see if there is any unfilled sections in the interior parts. So in summary, short shots is the incomplete filling of a mold part, resulting in an incomplete part or defect in the end product. All right, and the major characteristic of a short shot is that it has translucency. All right, the translucent color attribute, that gray attribute, to show that there's something missing there. You know, it's obvious in the simulation, but in this case now, as you can see, the flow is perfectly in order. From the colors are very, very clear indicators of a smooth production with high confidence. Now let's talk about still on the fill time. Okay, the fill time. So let's talk about the hesitation. What is hesitation? This is the filling of the thick section first. All right, because of the less resistance to flow. Okay, which can of course cause short shot, the one we previously explained. So hesitation has to do with the attribute of a simulation filling the thick parts and leaving out the thin edges. All right, I'm focusing on the thick parts. All right, if a fill time result shows a section where contours are closely spaced, hesitation may have occurred. All right, this is very, very important that we take note of. So hesitation can cause short if a thin section freezes off before the part is completely filled. Okay, and you should also know that hesitation occurs when the melt flow slows down or stops along a particular flow path, causing asymmetrical and unpredictable flow parts or patches. All right, so just take note of that. I've now explained short shots. I've also explained hesitation, still under the fill time results. Now let's move on to overpacking. All right, now what is overpacking? Overpacking during fill time occurs when extra material is compressed in one flow path whilst the other areas are still filling. All right, now part of what causes this is the high part rates, the warpage, the non-uniform density distribution. And you should also know that if a fill time result shows that one flow path finishes before others do, it may indicate overpacking. All right, overpacking can cause high part weight, of course, warpage, non-uniform density distribution throughout the path. This is very, very important. Now we're still on the fill time results, so let's look at the weld lines. Okay, weld lines actually are indicators of weakness or visible flaw made when two or more flows meet, converge whilst filling a part. Okay, now, and what we need to understand is that this clearly indicates structural weakness or perhaps a surface blemish from the mold design. So adjustments might need to be made. Now, another important thing you need to understand is that the overlay of the weld line result in the fill time is actually indicative of something to confirm their presence. So weld lines can cause structural and visual defects, and once they are spotted, they should be corrected. All right. So another important thing under this fill time is the air traps. This occurs where melt traps compress, bubble, of air or gas between two or more converging flow fronts, cavity as well. Okay, that's what air traps is. And additionally, overlay the air trap result on field time result can confirm. Okay, it's always good to confirm their presence. All right, that's the overlay air trap result in field time, because air traps can cause structural and of course visual defects. Now, finally, under the field time, let's talk about the race effect. This is when a molten plastic flowing it tends towards flowing to thicker regions easily than the thinner regions. Okay, this just like reminds us of the previous one we talked about, which is the overpacking. All right, and of course the hesitation too. So some of these things, these effects or these attributes you are seeing during the simulation time, they are interrelated. Okay, so the race track effect is when a molten plastic flows into thicker regions easily than to the thinner regions. The racetrack effect can cause air traps and weld lines. Okay, check the location and number of air traps and weld lines. This is very, very important, and you should take very important note of this.
Audio Jungle. Audio Jungle. Audio Jungle. Audio Jungle.
All right, so let's move now to the plastic flow. The effect, what happens during the fill time also is the same with the plastic flow. Right, now let's move to the confidence of fill. Now in this particular result section, which of course is like one of the functionalities of this object, all right, the confidence of fill results shows probability of plastic fills, how the plastic fills a region within cavity. All right, this is very, very important, and we should perhaps take note of that. Now there are certain things that come alongside with this results, this confidence of fill. Now if it shows green, the green, all right, the greenness that you can see there, that color green in this section of the Moldflow simulation result, it shows that there is high quality, okay, that the fill will actually go with at least over 90% of accuracy. All right, now for the medium, that is for the parts that might, you know, have a little bit of defect or might have difficulty in filling, having quality defect, you see the yellow indicator there. That's what the medium shows. And this, for this result, we are seeing about roughly 10%. all right, now then of course, if you talk about the low, you have 0% of defects. The redness, that red indicator, is a clear indicator that there won't be much of any defect in this simulation. All right, now let's look at some things to look out for here. It says if cavity does not fill and results in short, changes must be made to the design. So this particular part of the result is very important. Then injection location, choice of plastic or processing conditions. So that is if the cavity does not fill, if the confidence indicates that it doesn't fill, okay, and with the potential of resulting in a short, changes must be made to the design, injection location, choice of plastic or processing conditions. Now, to ensure the finished part is of good quality, the cavity must also be adequately packed with plastic. You must therefore determine not only whether the part will fill, but also whether a good quality can be made. So that is what part of what confidence of fill does. Now, if you're working under the advisor, all right, the advisor uses these two items for information to calculate the risks of performing or producing this part with the flowing sliding scale. Now, when you see the all green, like I said, the part is easily filled and quality should be acceptable. The part may be difficult if it is yellow. Now, the part may be difficult to mold or quality may not be acceptable as percentage of yellow increases. All right, so the yellowness must not increase, must be minimal, must be in its barest form. So this is very, very important. Then the quality of in molding parts will also increase and the part quality will decrease if there are some yellow, that is in the bottom. Perhaps some injection needs to be placed at the bottom there, you know. So then some yellow and red, the part will be extremely difficult to fill, or quality is likely to be unacceptable. As the percentage of yellow and red increase, difficulty in molding parts will increase and the part quality will decrease. So then the last one is the translucency, that's the color translucent. Now the part cannot be molded because of a short, that's the short we'll call the defect that we've all been talking about. Then the confidence is in three forms, like we rightly said. You have the high confidence of field. This high confidence of field indicates that the area of part has high probability of filling with plastic. All right, the medium of field indicates the area that the part may be difficult to fill with plastic. Then of course you have the low confidence of field. The low confidence of field indicates the area of the part which of course may be difficult to fill with plastic. So like in this case study now, I think it's better to work on the lower parts of this particular object, this particular 3D model that we are seeing, plastic model basket that we are working on. So that is that. This is very, very important. Okay, so having now gone through the confidence of feel, the next important thing we want to look at is the quality of the result. That's the quality prediction. Now this is derived from pressure, temperature and others, and what we also should take note of here is that the quality prediction result is used to estimate the quality of mechanical properties and the appearance of the part. This result is derived from pressure, temperature and other results. The colors displayed in the quality prediction results include and of course indicate the following. Now you can see the greenness here. You see this greenness now, and the percentage shows that the product has high quality. All right, now the next important thing to that is the yellow. If they are yellow, like you can see in this in the top part, especially where the ejection locations are, you can see that there are some yellow parts. So the yellowness indicates that there are quality issues associated with that particular part, that area in question, whilst the red actually indicates that the quality has problems that really need to be addressed before production. All right, but in this case now you can see that there is no reddish parts in the analysis results. Okay, so this is very, very important. And like I said, we ensure that you know the color indicators. All green shows that the part quality should be acceptable. All right, some yellow indicates that the part quality may not be acceptable. As the percentage of the yellow increases, okay, the part quality will decrease. Okay, here we're having just 12.9%, whilst for the green we have 87.1. So at least there is a high percentage of quality, while the yellow and red indicates that the part quality is more likely to be unacceptable. Okay, as the percentage of yellow and red increase, the part quality will decrease. All right, so these are very, very important things that we should take note of. Now, under these, of course, you also have the high quality prediction, the medium. You know, the red is the high, the medium is the yellow, while the low is the red indicator respectively. So this is all about the quality prediction. Now there is also a way which you can actually improve the quality result. Now the quality prediction result shows that there is a problem with an area, okay, of mold, and provides some sort of measure of the surface quality of the finished part. Okay, so now in this wizard, this analysis wizard, you can just simply go to the process settings and change some of these, maybe tweak some of the values like the mold temperature and the of course the melt temperature as well. You know, you can tweak them, and like in the next feature which you'll be looking at, the pressure drop, you'll be knowing the more important how these things are related to the quality result prediction. All right, so this is very, very important. So let's now head to the pressure drop and see what it looks like. Okay, so let's look at the pressure drop, having gone through the quality prediction. Now you should understand what the basics of the pressure drop results. Okay, this is very, very important. Now the pressure drop results shows a range of colors to show region of the highest to the least pressure drop. Okay, the pressure is needed to actually feel certain areas of interest of the parts. Now what you should note here is that for this pressure drop result, the pressure drop result uses a range of colors to indicate the region of highest pressure drop through the region of lowest pressure drop. All right. Now, we should also note here that the result indicates how much pressure is necessary to fill the different parts, areas of the parts. Okay, this is very, very integral, and you should take note of that. Now, as shown in this case study, which I'm actually using for this, for the purpose of this study, this research, the simulation research, you can see the color at each place on the model represents a drop in pressure. All right, the unit here is MP, so this is pressure actually. All right, and like I said, the color in each place in the model represents the drop in the pressure from the injection location. From the injection location, you can see from the injection. I have 5 injection locations here, and those 5 is, initiating at blue. It's bluish. So now from the injection location to the place on the model at the moment that the place was filled. Okay, this is very, very important, and it's something that we should take note of. Now let me play back the animation and see how this goes. This is the simulation animation of the production time. You can see that actions is being taken from the location, the injection locations, to the bottom parts of this paper basket. All right, the waste paper basket. So let me just play back that so you get to see it more clearly from another angle. You can see that it's going from top to the bottom. All right, so now it is very important that you get to understand how these colors are, what they indicate. So the pressure from the injection location to the place or the moment at the moment the place was filled. That is the pressure required to force, okay, to force material to flow to that point. That's what this is doing. It's just indicating. Now, here are some of the most important things that you need to take note of as far as the pressure result is concerned. Now, the pressure drop result is one of the factors that is used to determine the confidence of field result. That's the previous, the past immediate field previews that we took just before the quality prediction. All right. Now, so it means the pressure drop is actually proportionally related to the confidence of field results. Okay, this is very important. I'm going to elaborate more shortly now. Now, if the pressure drop is greater than 80% of the current value set in the maximum machine injection pressure at the analysis wizard process settings. Now, the analysis result process setting is this very one that I showed in the last explanation for quality prediction. This is the process settings. You can see that the melt temperature here is 50. Then the melt temperature, the mold temperature actually is 50. Then the melt temperature, you can see a series, a range of arrays there. The maximum is placed at 220. Okay, these are just the default values. Then also you can see the maximum machine injection pressure. All right, so now in relation to what we're talking about now, it says that for the pressure drop, okay, if the pressure drop is greater than 80% of the current value set for maximum machine injection pressure, this is the one he's talking about here, this very one you're seeing here where this cursor is moving around. Okay, so if the pressure drop is greater than this value here, 80% of the current value set here, as you can see, this causes yellow confidence of field. Okay, yellow, the yellow is this yellow you are seeing here, this yellow indicator here where you have the pressure at 21.57 as for this waste paper basket. All right, so like I said, if the pressure drop is greater than 80% of the current value set in the maximum machine injection pressure in the analysis wizard, this is the analysis wizard, the one you're seeing on the screen right now. Okay, this causes a yellow confidence of field. Whereas on the other hand, if the pressure drop reaches 100% of the current pressure limit setting, Okay, this is another condition. Now this is an alternative condition, okay, taking place if the pressure drop reaches 100% of the current pressure limit setting. All right, the confidence of field result for this area is red. Okay, so that's the condition. So that means that for this part here, as you can see in the animation, and this animation that you're seeing here, and I'm going to play back now. Now you can see that the reddish comes just around the bottom parts. So that means that for this region, it just simply means that the pressure drop has reached 100% of the current pressure limit setting. Okay, so some sort of things might need to be done. Okay, so just right before that interruption, I was talking about the reddish part. Now this reddish part, like we've said, indicates that the pressure drop has reached 100% of the current pressure limit settings. Okay, and the confidence of field result for this area is red. Okay, so having said that, we should also know that if the default value of 180 pressure, that's MPE, 180 pressure for maximum injection pressure limit is higher than the actual molding machine capacity, the confidence of field result will be better than is actually expected. Okay, what it means is that if the default value of 180 for the maximum injection pressure limit is higher than the actual molding capacity, the confidence of field result will be better than is actually expected. So what it means is that the settings, the default value for the pressure settings is very, very critical. Okay, and it also affects the confidence of field results. So that's what we should also take note here. Now, some molding machines can inject material up to 200 pressure, okay, value pressure. So in knowledge of typical performance of machines, that's the CNC machines in question now for the production of plastics. Okay, the physical performance of the machines used in production can help you determine the viability of the pressure drop results. Okay, so this is very, very important. The pressure is connected to the confidence of field, okay, which shows the quality of the part in question. All right, now a high pressure drop can also indicate hesitation, so you should also take note of that. I spoke about hesitation in the field results. Okay, so you should take note. Or some other difficulty in filling a particular area of part of the part. Now let's look at still under the pressure drop. We're going to try and look at some of the things to look out for. Okay, now you should take note of this. Increase the maximum injection pressure to improve the confidence of field, just like what I said previously. So this pressure is actually connected to the confidence of field. So in order to create a better confidence of field, the maximum injection pressure should be increased. All right, now another important thing that we should take note of is that moving polymer injection locations closer to problem area or add additional injection points to improve the likelihood of all sections of the part filling. Okay, so the polymer injection location, so that means what it's simply saying is that the injection locations can also be changed. Okay, it can be flipped. Maybe like I used just the top, you can actually change in another scenery. You can swap or change, redesign the positions of the injection locations so that the likelihood of filling the parts will be more accurate. That's what that means. Now another thing to also take note is that after the part geometry, complex and thin geometry, okay, you can alter these things. That's the part geometry, the complex and the geometry variables, thin variables, okay, because these can cause filling difficulties that require high injection pressure to complete the filling. That's, it's just trying to say that you can also alter the part geometry, okay, based on the certain complex thin geometry, which can cause filling difficulties that require high injection pressure to complete the filling. Okay, So the next important thing we should take note here is that you should also you can also select a different material with higher melt flow rate, so that the injection pressure is required, okay, so that the injection pressure rate is required to fill the parts. Then finally, you can also increase the melt temperature to reduce the viscosity of the melt and enable melt flow into the mold more easily. Okay, these are very, very important things to take note as far as the pressure drop is concerned. Pressure drop is very, very important. It's connected to the confidence of fill. You should take note of that. Confidence of fill again is determined by both pressure drop and melt temperature. That's the two variables. Pressure drop and melt temperature, they are very, very much interconnected. Okay, so and they affect the confidence of fill, which of course is the probability, holds probability of quality, overall quality of the parts. Now you may also need to adjust both processing conditions before at an acceptable confidence of fill, or before an acceptable confidence of fill is determined. So that's also about the pressure drop. Okay, so from the pressure drop now we're going to advance to the temperature at flow front. Okay, you can see the animation going from the bottom up. All right, now in this stage we're going to look at what these color indicators mean, okay, for the production time. This is very, very important for you to understand the interpretation of these colors and what they actually represent. Now the temperature at flow front result, okay, is produced by a field analysis. Okay, this is part of a field analysis, as you can see on the screen. Now it shows the temperature of the polymer when flow front reaches a specified point in the center of the plastic cross section. So we're talking of cross sectionality now. All right, it's, if you observe, this is coming from that bottom to top. All right, as you can see, and the measurement there is in degrees since it's temperature. All right, now as shown in this specific basket project that we're working on for this particular case study, the temperature at flow front uses a range of colors. You can see the range of colors there. The indicators there, you can see blue to green and upward to yellow and red respectively. It uses a range of colors to indicate the region of lowest temperature in blue. Okay, the lowest temperature in blue, you should take note of that, through the region of the highest temperature. Okay, I think that should be in the red. Yes, as you can see there, you can see in red. So the color indicators there, I hope you're taking note of what it means. All right, the highest is in red. Okay, and from the lowest there, the lowest seems to be in some sort of blue greenish. All right, so now let's go on. Now the colors represent the material temperature at each point, okay, as the point was filled. The result shows the changes in the temperature of the flow front during filling. Okay, the flow front, it shows the result of the temperature of the flow front. This is very, very important for you to take note of. Now the flow front temperature should not drop more than 2 degrees. Okay, as you can see here, to 5 degrees during the filling phase. This same filling phase that you can see here, you can see that it goes from 204.6 all the way to 220, what was indicated in the analysis wizard that I showed previously. Okay, the filling phase. Now larger changes often indicate that the injection is too low. Okay, or there are areas of hesitation, the same hesitation that I explained earlier, that has to do with faulty parts. Now if the flow front temperature is too low in thin area of parts, hesitation may result in a short. All right, So we should take note of that. Now, in areas where the flow front temperature increases by several degrees, all right, material degradation and surface defects may occur. So this is another very important part, all right, that we should take note of. It says in areas where the flow front increases by several degrees, okay, by several degrees. So this might indicate that material degradation and surface defects may occur. Okay, so that means this form of alteration might still need to be done before this particular case study is put into production. All right, now let's look at further how this result can be utilized. Now, minimize the flow front temperature variation in the filling phase to under 2 to 5 degrees Celsius. Smaller temperature variations cause fewer problems. So what this is saying is that perhaps in the flow front temperature variation, you can actually minimize 2 to 5 degrees. Smaller temperature variations can cause fewer problems. Yes, it's very important. So the lower the temperature settings at the beginning, the better the quality is. Now let's see. It says also that you should try to change the following settings to improve the results using information in the table, okay, that you might have drafted, okay. A table that might contain the problem. Let's say, for instance, temperature is low. The change might be to decrease the injection time. All right. Then the other thing that we're seeing here is possible problems may cause excess shear in the gate if it is restrictive. Too much shear will cause degradation and surface defects. Now, you can also increase the melt temperature, and this may increase cycle time. It may also cause material degradation. Also, you should then also take note that you should keep the temperature within the temperature limits. Okay, as far as the temperature flow front is concerned. Then also you can also know that the specified material information in the database to take note of the variations, the optimal values for existing product, the model. Because in the last training exercise that I had with the engineers from the NEDI Institute, I did mention that there are specific models that have been made. So you can improve on an existing model. I did this because I really had a little bit of time explaining this aspect to the participants. You need to know the standard settings for existing products that are in the market, so you can now make research on what to do to improve them. And this will actually save you time of reinventing the wheel. If you make a little adjustment, adding value to knowledge. I made so many analogies about modeling, in the training that was held last. Okay, the Sending Lady conference that we held for the engineers, where we talked about extensively the use of models. Some of the participants were actually emphatic on building their own model. There's nothing wrong about building models. You can build your own models from the scratch, but what the world has gotten to now, there is a huge knowledge base that researchers, you as a researcher, can draw from. You don't need to go to, like, okay, let me give you an instance. That you want to produce a car, you want to start a car company, or you want to start a manufacturing company for okay, so other things you can do is you can increase the thickness of the area to permit flow. Okay, now the effect might be that this might cause functional problem and design to increase the cost. Now, I did mention that for instance, if you are creating a model, maybe you have a project you want to create a plastic bottle, or you want to create this. Now, I give instances of models. You want to create, let's say for instance, you want to create a car, you want to start a car company. It won't be too wise for you to go back to the 1800s, or perhaps when car was not even invented, and then you start. You can actually do that, but I think that would be too exhausting. So what scholars have done, like in computer science now, we have a lot of what we call libraries. We have models, we have modules, we have application programming interfaces. These are specific resources that have been made for you to do a lot of permutations, perhaps in mathematics. Okay, let me not even talk about ChatGPT. ChatGPT now is a large language model. It has, it's more like an internet of things, of languages. Whatever it is you can think about in language, in the context of language, everything ChatGPT does it. Whether you type, whatever issues you type in terms of language, whether it has to do with financing, health, education, whatever it is you want, ChatGPT has a way of giving you unique answers that is different for any existing answers on the internet. And that's part of what makes it simple. So where computing is going is about using existing models and adding value to it. All right. For instance, okay, I give you an instance of a car. You want to start a car company, you don't need to go to 1800s or 1500 or the first century to do that. All you need to do is there are open source cars models that are existing in so many places, and when you take these models, you can decide to probably create a Jeep. So the model of Toyota Jeep, you can look at it, study it, see some maybe parts you can make improvement to. So you make reference to the model, maybe RAV4. Then perhaps in your own version of RAV4 you could add make some kind of thing that is different from the existing. So, but at least making a basic foundation or reference to the model that you are building on. This is very important so that you will not be doing plagiarism. So this Moldflow has several models that you can draw from, look at their process settings, and see how you can import it into your existing work so that you can improve your analysis results, okay, and the accuracy of your model. Now, before we wrap up for this temperature at flow fun, I want you to take note of things to look out for. Okay, now when viewing the temperature at flow results, you should look out for the following. One, the hot spots. Usually these exist around the gate in the area where excessive shear heating occurs. All right, then the cold spots indicating hesitation too must be noted. Then you should also check whether the material is shear heating or is it excessively outputting. So these are very basic things that you need to know as far as the temperature at flow front is concerned. Let's now move to the next thing, which is the average temperature results. Okay, so let's now look at the average temperature results. Okay, we can look at the average temperature results and try and play back that. Now you can see the animation taking place from the bottom of this model to the height of the model. All right, so here we need to take note of certain things that draws basic attention. Now the average temperature result indicates the average bulk temperature through thickness of the parts at the end of field. This must be noted. Okay, so the temperature of polymer melt changes not only with time and location, but also with thickness during the entire injection melting cycle. All right, you should very well take note of that. Now you should also know that it is difficult to illustrate all these changes in a single display. All right, rather the average temperature is used to indicate its weight across the thickness. All right, average temperature represents the energy that is transported through a particular location at a specific time. All right, now hotspots, which are due to excessive viscous heating during the filling stage, are indicated on the average temperature contour. All right, so you can see this is all about temperature. Now let's look at how we can actually use these results, okay, for production time. Now you can use the average temperature result in an alternative way of examining the flow distribution. All right, areas with continuous flow heat convection, all right, typically have higher average temperature, which drops quickly when the flow in that area, stops. So if average temperature is too low in a thin area of the parts, all right, hesitation or shorts can occur. You should take note of that. If the temperature, all right, if the temperature is also too low in that area where the weld lines are present, the weld lines may be worse. So these are conditionals that you need to take note of in these results. Now furthermore, in areas where average temperature is too high, material degradation and surface defects may occur. All right, so in order to alleviate these effects, you should ensure that the average temperature is always within the recommended temperature range for the polymer you are using. And this brings us back to modeling. There are standard models. If you are tweaking the variables for your production, you should always consider the existing models that have worked, and make your research, your own personal findings, to ensure that yours will not be a defective model against existing models in the market. It should be an improvement to the existing model so that it will have market value, because all these efforts, of course, still tends to utility, satisfying end users. So you wouldn't want to produce something that is less than what is already existing in the market. This is what all this effort is about. So if I'm to recap that, in areas where the average temperature is too high, material degradation and surface defects may occur. So in order to avoid this, okay, ensure that the average temperature is always within the recommended temperature range for the polymer you are using. Okay, you may also consider redesigning the part geometry near the hot spot or changing process conditions. Now, differential temperature can also cause non-uniform shrinkage and warpage. All right, now furthermore, the average temperatures results should be examined in conjunction, all right, in conjunction with frozen layer fraction at the end of field results. Any section of the mold with an average temperature that is below material transition temperature and frozen percentage of greater than 25% may not be packed properly, which can lead to shrinkage and warpage problems. So these are very basic things that you need to take note of. Now I want to talk about the things that you need to take note of under this average temperature results. A number of options are available to improve these results. Okay, alternatively, usually you should have side effects. So after making or altering changes, you should check to see if other problems might have also been created by your change. So these are points to take note of. You cannot be too sure of modification. For each modification, there might be other issues that might arise. So you need to be very, very careful about that. This is very, very important. Now, like I said, the number of options are available to improve results. Alterations have side effects or after making changes. So these are some of the things that you can look out for. Now, for the temperature, for instance, if the temperature is too low, increase the melt temperature. The possible problems that might come from this might increase the cycle time. It might cause material degradation. It can also make the temperature or stagnant. Okay, within the temperature limit specified in the material information in the database. All right. Now the other thing is increasing the mold temperatures. You may increase cycle time. All right. Now the other thing is decreasing the injection time, and the effect might be this might cause excess shear at gates if it is restrictive. Too much shear can cause degradation and surface defects. Now the other thing you should take note is increasing the thickness in the area to permit flow. This might cause functional problem with design and increase the cost. All right, so if you are increasing the thickness of the area to permit flow, this might also cause functional problem with design and increase the cost of production. Now for hesitation in thin areas, you can refer to the part of this video where I talked about hesitation. Now the other aspect to affect this is the moving away from the hesitation area. This may cause hesitation in other areas of the part. Then the other thing is you can also increase injection time, and the side effect might be increasing the cycle time. These are things that particularly affect the average temperature. So let's now move to the next thing. All right, so now having been done with the average temperature, let's now try and move to see the next result, which is the time to reach ejection temperature results. Okay, as you can see now, let's just play back the animation and see how this goes. You can see the field going on there from the bottom up to the top. All right, as you can see there, that went pretty smoothly all the way down up. So now what we should take note is this. We're talking about the time to reach ejection temperature. All right, this result actually indicates the amount of time that it takes to reach the ejection temperature, which is measured from the start of fill, as you can see in the animation that we're using here. All right, for this case, this is in seconds, so we have from 0.7053 all the way to 5.34. okay, so that's that. Now if the part has not frozen by the end of the cycle time provided, that's the cycle from the 0.7 to 5.340, okay, a projected time to freeze is displayed in the results. For a dual domain, okay, I was talking about dual domain in the previous videos of Autodesk Moldflow. Right, I really made difference between the dual domain, the 3D, and of course the mid plane. All right, the most popular is the dual domain, which is used for the thin parts, and the 3D mode, which is actually made for the thick parts. Now for the dual domain analysis, the value displayed in the time taken for 100% of the local thickness to the injection temperature. All right, that's for dual domain. Now let's talk about the 3D flow. Okay, now for the 3D flow, all right, the value displayed is the maximum time over the local thickness mapped from the interior to the surface of the part. All right, so you should take note of this. Now you should also note that the result takes into account the dynamics of the packing face. All right, the packing face, and when new hot material enters the cavity, this new hot material affects the cooling time. You should take note of that. Now let's look at how this result is actually utilized. Pragmatically, this part should freeze uniformly. All right, uniformly, like what you see in this animation. It's the flow is just seamless. It's going uninterrupted. So that's what it means, that it freezes uniformly. Areas of the part that take longer to freeze may indicate thicker areas of the part, or areas of shear heat during the filling or packing. All right. Now, if it takes a long period of time to reach ejection temperature, this might often be caused by thick areas of the parts. Okay, so you might actually consider remodeling the part, maybe redesigning the mold itself from the source. Now, long periods of time are due to shear, and this might be difficult to solve. So reducing the shear might cause time to reach ejection temperature to adversely affect volumetric shrinkage and warpage. Alright, the time to reach ejection temperature result can also be used in conjunction with the cooling time variance results in that to diagnose and non-uniform cooling. So these are things that you really need to take note of as far as the time to reach ejection temperature is. Now, furthermore, if the resulting values for the parts as a whole appear high, that's overall it's high, you can also take action to reduce the cycle time, okay, and also reducing the mold and melt temperatures respectively. Now, this result will help to design cooling layout for detailed analysis of parts using cool analysis. If you can check the time to reach injection temperature result for a kind of presumptuous or assumed corrective action. So correctiveness modification is what today's technology is all about. You don't reinvent the wheels, you improve on existing technology, because the world now, like what they call this generation Gen Z, everything is about just adding value to it, creating new content to existing content. You can see people are generating content from existing content, so it's also part of what we're talking about as a corrective action. Now, before we move on to the next part of this, let's look at the things to look out for under the time to reach injection temperature. Now, is the part sufficiently frozen at the end of the packing? Okay, and cycle time. These are research questions you need to ask yourself. Is the gate freezing off too early before cavity can be adequately packed out? And then also, are these thinner regions freezing off before more extreme thicker regions, thus preventing the thicker regions from being adequately packed out? So these are basic things that you need to ask yourself whilst considering or observing the time to reach ejection temperature. Okay, so now that we are done with the time to reach ejection, we now advance to the air traps. Let's quickly look at what this gives us as far as the simulation animation is concerned. You can see that this is just giving us some sort of translucency. Now, what are air traps? Okay, air traps are triggered when the melt traps compresses a bubble of air, okay, or gas. Right, I spoke about this earlier in some of the trouble spots of a model, of a plastic model. All right, so between two or more converging flow fronts, all right, or between the flow front and the cavity wall. Now, what you should take note is that in a very, very common atmosphere, the result is a small hole or a blemish on the surface of the parts. In very, very rare cases, the compression increases the temperature to a level that causes plastic to degrade or burn ultimately. So these are things that you need to put into consideration. Now, other things you should also note here is that the air traps are often due to converging flow fronts caused by racetrack or hesitation effects, all right, like I previously said, or by non-uniform or non-linear field patterns. Non-uniform or non-linear field patterns. Even the part has flow paths, the part that has flow paths, okay, inadequate venting, that's ventilation, can cause air traps to occur at the end of the flow paths. Okay, so These are very, very critical information that needs to be noted under the air traps. Now let's now look at how to really use these results. Now, air traps indicates how severe air traps can be or will be, and where they are likely to occur on the parts. Okay. Now, air traps can also be acceptable if they occur on a surface that does not have to be visually perfect. Alright, so you should take note of that. The field time result is used in conjunction with air traps result to confirm feeling behavior and assess the likelihood or the possibility of air traps appearing. Now, additionally, the air trap plot is used to determine probability of air trap during a particular location. A higher value, okay, a higher value, you know, clearly shows a higher probability that an air trap will occur, and a lower value indicates a lower probability that the air trap will occur. All right, you can see the air trap says at 1. So you know, since the this is a basket, a waste paper basket, airs are likely, of course, to go in and out because that is how it is designed. So now the air trap results can reveal the following problems on your specific model parts. Okay, burn marks caused by air in an air trap, which ignites under pressure and burns the plastic. Now, short shots caused by incomplete filling of the part. If air trap is not vented and not compressed quickly enough to cause a burn mark, it may cause short shot or leave bubbles of the air gas in the plastic part. Then the other surface blemishes caused by air traps. Now let's now look at things to actually look out for. These methods I'm about to mention can be used to prevent air traps. Number 1, you can use flow leaders or deflectors. Alright. 2, you can also increase the injection speed to eliminate air traps caused by converging flow fronts and excitation. Alright, so then furthermore, you can also decrease the injection speed to reduce air traps caused by poor venting and prevent burn marks. Alright, so here also you can decrease the wall thickness ratio to reduce race tracking, like the race tracking I mentioned earlier. Then also you can move the injection location so that the air traps from those areas that are easy to vent, which of course contributes to the pattern plane. So modifying injection locations is very, very key, and you know, can also be of great use in the overall perception or simulation result for any product, not just this alone, but anyone. So the next thing we're going to be looking at now is the weld lines. Alright, so from the air traps, let's now move to the weld lines. Okay, these are the weld lines. Let's run some animation there. You can see the weld lines strategically being placed on the part. Okay, now the weld lines result displays the angle of convergence as two front folds meet as flow fronts or meet. The flow front means, you know, the rising of specific activity within these planes. Now you should also take note that the presence of weld lines may indicate structural weakness and also a surface blemish. Okay, now take note that by overlaying the field time result and stepping through the animation, you can see how these full fronts converge, just like what I just did now by animating, and you're seeing the convergence from the strategic locations, and you can see that it's taking place from the bottom of the object up to the top of the where the locations injection, the 5 injection locations are. Now the term weld line is often referred to as to mean both weld and milled lines. The only difference between them is the angle at which they are formed. Alright, Weld lines form at lower angles than meld lines. So, like I said previously, the weld line you can see coming, they are taken from the bottom to the top. Okay, and it's rising to the top where the locations are, the injection locations are. Now, weld lines can cause structural problems and make your part visually unacceptable, but they are unavoidable when the flow front splits and comes together around a hole, or if the part has multiple gates. All right, those are the conditions that are related to weld lines. Now, let's consider processing conditions for weld lines to determine whether the weld lines will be of high quality. Now, weld and meld lines should be avoided, particularly weld lines in areas that require strength or smooth appearance. Now, let me also state here that for mid-plane or broad domain research studies or parts, this result is the same in custom weld line plots with melting angle of 135 degrees for a different meeting angle. All right, now you can actually create custom weld plots and specify the meeting angle. This is very important. Now, you should also know that processing conditions help to determine the quality of the weld and meld lines. Okay, weld line strength is influenced by temperature at which the weld line is formed and the pressure exerted on the weld until the part freezes. Pressure is zero and the time the weld line forms. Typically, a good weld will occur if temperature of the melt weld line forms at more than 20 degrees Celsius below the injection temperature. Now let's look at how we can furthermore use these results. Okay, using these results is very key and could help in interpreting the predictability of these products. Now, weld lines can be moved by changing field pattern to make the flow fronts meet at different places. To move the weld lines, you can actually alter the gate locations. You can change the thickness of the parts. All right, changing the thickness of the parts, can actually be something that can be useful as well, just to reduce the weld lines. All right. So now, in order to improve the quality of weld lines, okay, you can increase the melt temperature, the injection speed, or the packing pressure. Okay, those are ways in which to reduce weld lines. This will enable the flow fronts to weld to each other more effectively. Now, the other thing you should do is you could increase the diameters of gates and runners to make it easier for the pack. Okay. Now, you can also move the injection locations to make weld lines form closer to the gates. Alright, the weld line is then created with higher flow front temperature and is packed with more pressure. So these things are of great importance. Now, you can also place a vent in the area of the weld line. Alright, a vent, that's you're talking of airspace. Okay, now this will remove the air traps, which would further weaken the weld line. Now, you can also optimize the design of the runner system. Then you can reduce runner dimensions and maintain the same flow rate. Shear heating can then be utilized to increase the melt temperature at flow fronts. Alright, so now solving one problem can introduce other problems, like I said previously, to the injection molding process. So you should, this thing requires extensive care and research on your own, personal research. You read papers, you read about products, existing products, perfected products that have high customer utility indexes. And this information is usually are available online that you can check. Now, one of the things you can check for are that the Weld Lines result helps you to identify the following problems. For instance, structural problems. The part may likely fracture or deform at a weld line. Now, particularly if the weld line is of low quality. The weakness is more serious problem in areas of the path that are subject to stress. Now, visual defects. A weld line can cause line, notch, color change on the surface of the parts. If the weld line is positioned on a non-critical part surface, such as bottom, this may not be a problem. Alright, so we're talking at weld line showing us being indicators of structural problems and visual defects. So these are things that need to be really put in their perspective. Alright, so the next thing we're going to be looking at is the injection pressure. Alright, so from the weld lines we are now going to move to the injection pressure results. Okay, and this is what it looks like. This is the result of now let's play the animation and see. You can see that the movement is taken from the bottom to top. Alright, with very clear color indicators. So let's look at what this does, and how we can use it for the simulation process of this plastic. Now let's go. It says that the injection pressure results is produced by field analysis. That's the basic concept of the injection pressure. Alright, and it indicates the maximum injection pressure value obtained before the velocity pressure switch over occurs. Alright, velocity pressure switch over occurs during the filling phase. Alright, the filling phase is just like a basic basic part of this production process. Now, the pressure at the end of the field result, which is produced by field analysis, indicates the pressure distribution in the cavity at instant when the cavity is completely filled with polymer. Alright, so we should take note of that. Then at the beginning of the filling, the pressure is 0, okay, or let's say 1 atmospheric pressure in the absolute pressure scale throughout the mold. The pressure at a specific location starts to increase only after the melt front reaches that location. Alright, so the pressure continues to increase as the melt front moves past. Okay, it moves past due to the increasing flow front between specific location and the melt front. The pressure difference from one location to another is the force that pushes the polymer melt to the flow during filling. The pressure gradient is pressure difference divided by the distance between the two locations. Like water flowing for instance, water flowing from higher elevations to lower elevations, polymer always moves to the direction of a negative pressure gradient. Alright, this is very critical, from higher pressure to lower pressure. Therefore, the maximum pressure occurs at polymer injection locations and minimum pressure occurs at melt front during the filling stage. Okay, as shown in this plastic model that we are actually looking at. Okay, so these are very critical areas that we need to take note of. Alright, now we should also take very critical note that the magnitude of the pressure or the pressure gradient depends on resistance of the polymer in the mold. Alright, and this is due to the fact that polymer with high viscosity requires more pressure to fill the cavity. Alright, so you should take note of that. Now, restricted areas in the mold, such as the thin sections, the small runners, as well as the long flow lengths, require larger pressure gradient and therefore a higher pressure to fill. This is very critical, and it shows that this particular variation, this injection pressure, just has a lot to do with the field analysis. Now let's look at how this result can be utilized in a productive way. Now during packing, pressure variations affect the volumetric shrinkage. During packing, pressure variations does have direct effect on the volumetric shrinkage. The pressure variation in cavity also can be minimized during the packing stage. All right. Now another important point to note is that the injection pressure result is used with pressure drop. All right. Result to locate areas where actual injection pressure is too high. All right. Now let's look at things to watch out for. These options can be used to solve problems with underfilling or overpacking caused by injection pressure. Alright. 1. After the injection location or with the effect of the additional injection locations to fill the area. Alright. You can alter that. You can alter the injection location. Additionally, you can also use additional locations to fill the problem area. Alright. So the number of gate locations depends on part geometry, material and processing conditions as far as this result aspect is concerned. Now another important thing you need to note is that position gates to create balanced filling pattern and uniform pressure distribution. Then you should avoid placing gates close to thin areas that will cause hesitation and areas that will fill early and overpack. Alright. After that, part geometry. You can also alter the part geometry. Okay, so these are very critical steps that you can take. Now, furthermore, you should also know that if changing the gate location to lower injection pressure is not possible, you can redesign the part to increase the wall thickness. This seems to be a general solution to most of these problems that has to do with short hesitation and other production time issues. Now, a complex and thin geometry can cause filling difficulties and require high injection pressure. You should take note of that. Very important. Okay. Now, you can also select different material with lower viscosity, which requires less injection pressure to fill the molds. Then, additionally, you can increase the melt temperature to reduce the viscosity. Ultimately, this reduces the injection pressure process requires to fill the mold. Then, you should also look for particular areas that have the following issues: hesitation, overpacking caused by high injection pressure, as well as the shrinkage. Alright, this is very important. So the next thing we'll be looking at now is we're going to be looking at the frozen layer fraction at end of fill results. Okay, so having completed the injection pressure elaboration and thesis, the next important thing that we want to handle here is the frozen layer percentage at end of fill. All right. So now, let's look at the outcome of the results. Okay. I mean, let's just test run the fill analysis and see what is going on here. You can see that the fill is going on upwards from the bottom of this object. Okay, and it's going up from a very low percentage to at least 26.30 in percentage. All right, so now we need to understand something here, and what we need to understand is the fact that the frozen layer fraction at the end of fill indicates the thickness fraction of the frozen layer at the end of filling. At the end, okay, you should take note of that. Now it ranges from 0 to 1. That's just like saying from 0 to 100%. All right. Now a higher value indicates a thicker frozen layer or thinner flow layer. Okay, and higher flow resistance. Okay, so now we should also take note importantly, that a polymer is considered frozen when the temperature falls below the transition temperature. That's in T-trans. Alright, so in this case we are looking at a range between 0 and 26%. Now we should also take note that during filling, the frozen layer should maintain a constant thickness.
Audio Jungle. Audio Jungle.
Try to say in essence is that during filling, the frozen layer should maintain a constant thickness for those areas with continuous flow. Okay, because this is due to the fact that heat loss to the mold wall is balanced by hot melt. Okay, so let's quickly talk about the frozen layer fraction at end of fill results. Now, the very basic thing we need to understand here is that this frozen layer fraction end of fill results represents the thickness of fraction of frozen layer at the end of filling. All right, now it usually ranges from 0 to 1. That's like saying from 1 to 100%. Its metric is in percentage. You should very well be very aware that a higher value indicates thicker frozen layer or thinner flow layer and higher flow resistance. Okay, that means that if it has higher values, it indicates or shows that a thicker frozen layer or thinner flow layer and higher flow resistance. That's the proportionality of a higher value is equivalent to a thicker frozen layer or a thinner flow layer. Okay, thicker frozen layer or thinner frozen layer and higher flow resistance. If polymer is considered frozen when temperature falls below the transition temperature, that's T-trans. All right, now very importantly also we should note here that during the filling, the frozen layer should maintain a constant thickness for those areas with continuous flow. This is because the heat loss to the mold wall is balanced by hot melt coming from upstream. All right, now you should note that once the flow stops, the heat loss through the thickness is completely dominant in that area, and also that a quick increase in the thickness of the frozen layer results from these effects. Now, furthermore, frozen layer fraction has very significant effects on flow resistance. The viscosity exponentially increases with decreasing temperature. That's the viscosity, right? Now, the thickness of the flow layer is also reduced as thickness of frozen layer increases. The effect of thickness reduction can be roughly estimated with definition of fluidity with representative shear rate. The fluidity is proportional to the cubic power of the part thickness. All right, that's we're talking about direct proportionality, between the fluidity and the cubic power of the part thickness. That's in this case now the waste paper basket thickness. Then we should also note here that a 50% reduction in part thickness reduces the fluidity by a factor of 8 or increases the flow resistance by a factor of 8. This is reminding us of what we learned in physics, action reaction forces. Okay, to every action there is an equal and opposite reaction. Now, moreover, we should also take note that 50% reduction in thickness in runners reduces the fluidity by a factor of 16. It is not surprising also that excessive high pressure is required to fill gates in which hesitation occurs early in the filling stage. The flow layer becomes very thin in areas of hesitation, which are filled last. Now, let's look at utilizing these results. The frozen layer fraction generally will be very low near injection location and end of fill. The maximum frozen layer fraction at the end of field should be less than 0.2 to 25. That's like 20% to 25%. In this case, we are having almost 26. We have up to 26%. So definitely this requires some sort of tweaking or modification so that these baskets can be optimized for production time. Now, higher values will make the part difficult to pack out. Areas of the mold that are filled early in the cycle but have little subsequent flow normally have highest frozen layer fraction. Now, let's take a look at very important things to look out for as far as this particular analysis result is concerned. Firstly, none of the parts should have frozen layer fraction that is higher than 20 to 25%, like I stated earlier. So the cutoff mark for the percentage should be 25. Anything higher than that will call for modification at the end of field. So a faster injection time will reduce the frozen layer fraction. You should take note of that. Then secondly, time to reach ejection temperature result is also indicated by these analysis results. Now, if hot spots are occurring, take the instance of looking for ways to cooling the circuit design. So this is all about the frozen temperature percentage at the end of field, and I hope you've been able to put down one or two important things that are of great importance. Alright, so the next important thing I want us to look at is the growth form results. And then under this section, we should try and understand the importance of the growth form results. Now, this is produced by a field analysis, and it indicates areas that are filled from each gate in multi-gated parts, so that you can determine whether the flow within the part is balanced. Alright, that is what this growth form result does. Now, furthermore, we should also take note that a growth form result indicates uniform filling wall will be balanced, just as you are going to see in this demonstration that I'm giving to you now. A growth form result that indicates that different gates are trying to fill at the same time of the part will be unbalanced. Okay, that is if the growth form result indicates that different gates are trying to fill at the same time. Okay, but in this case now, from the animation that we are playing and you're seeing right here, you're seeing that the filling of the gates are in sequence, in successive sequence. One finishes before the other picks up and finishes. So definitely there's a high level of confidence in this particular growth form results. Okay, now we should also take note that non-uniform filling, that's the one in the left, and uniform filling from the right are shown in the basket. As you can see, the values are strategically from 1 all the way to 5. That's the index 1, 2, 3, 4, and 5 respectively. Now, the growth form result indicates or applies numbers to verify these indexes to identify the gate in which the polymer was actually injected, so that when the field analysis is complete, this can be well defined. Now, when the analysis is complete, the growth form result indicates filling pattern of the part and indicates also which specific locations of the part are filled from which gate. All right, like in this case now, in this waste paper basket, we have 5 injection locations, and you can see the color indications from each of the injection locations. The colors are there. You can see blue, you can see red, you can see yellow, and some other colors there. About 5 colors to indicate the gate areas. Now let's look at using this result. The gate location analysis results can actually determine more appropriate gate locations in your part model, and the growth form result can also be improved in a number of ways. Now, furthermore, alterations usually have side effects, so after making changes it's very important for you to actually cross-check to see whether there are other problems that have been introduced due to your alterations. Now, let's take a brief look at problem and possible resolutions. For instance, if you have unbalanced flow patterns, which can be caused by one, polymer filling more quickly from one gate, two, polymer from both gates trying to fill at the same part, or a weld or mold line in a very sensitive area. Now, the resolutions to these are one, you could try and change the injection locations to achieve a full balanced fill pattern. You can also redesign the geometry of the model in the problematic area. Then you can alter gate positions, change the part thickness, increase melt and mold temperature, increase ramp speed, that's random access memory. Now, I cannot emphasize the importance of your system requirements. When you're running simulation, you need at least a minimum of 8 gig RAM. I don't recommend you using a RAM of 4 gig. It's a little bit ridiculous. You're running simulation with that kind of system configuration. You need something higher than 8 gig. 8 gig from above is sufficient so that these things will not run down or crash your system while you're trying to simulate. I talked largely about this during the workshop with the Ascending Neti staff members who attended the workshop in 2023. Now, the last thing that you can use to resolve or as a resolution to these problems is optimizing runner system design. This is also very important. Now, let's look at quick things you can look out for. One, you can see that the result indicates an equal distribution of colors, which will have uniform filling pattern and be balanced. If the distribution of colors is not equal, then the flow is unbalanced. In this case, the distribution of colors that we're seeing in this basket is balanced, and it is in sequence, in complete sequence, successive sequence. One finishes before the other picks up. So these are very basic things that you should look out for.
Audio Jungle.
Understanding Autodesk Moldflow Injection Advisor 2024 molding results. This is a special case study for plastic paper basket, a presentation by Hands On Lab Software Academy. Now, these are the brief table of contents that we'll be covering. Firstly, we have fill time and the plastic flow results. We're going to be seeing more about that. Then the confidence of fill, the quality prediction, pressure drop, temperature at flow front, average temperature, time to reach ejection, air traps, weld lines, ejection pressure, frozen layer at end of fill, as well as grow from. Now, the basic thing we should know is that this is an active summary of the video that you've just seen. and
Audio
you
Jungle.
should pay close attention to the active summary. What I did was that I picked the most important parts of the illustration that we just wrapped up now, and I'm going to be going through each of them in a logical sense and logical manner. Now, this is the fill time and plastic flow results. Now, these are the major things you need to be aware of. Firstly, you have the short, which of course is usually defined as incomplete filling of mold part cavity, resulting in defective outcome. Alright, the other one that fill time and plastic flow results can easily give indicators to, rather, is hesitation, which of course is the filling of thick parts first due to resistance to flow. Then overpacking. This is compression of parts in single flow part as a deviant. Okay, what this simply means is, like I explained during the analysis flow, overpacking is the compression of a part in a single flow part. All right, and the single flow part is the thick part of the model in question, the SDY project in question. And why Autodesk Moldflow does this is because it finds it more comfortable to go through the thicker parts than the thinner parts. All right, so when this happens, it's usually called overpacking. Then the weld lines or visible floor mode, just like what I explained previously. This happens when two or more flows meet during filling. Then the air traps. This is the effect of melt traps, compression, bubble air gas in flow fronts, just like I explained previously. All this is taking place, and these are indicators that fill time and plastic flow can easily reveal. Then the racetrack effect. Molten plastic flow or movement into thicker locations than to other parts of a mold. Alright, that is what racetrack is about. So let's go now to the confidence of fill. Under this, this is actually more like a probability distribution when you have, figures being given or indexes being given and indicators that are colored. All green usually means it indicates mold parts filling without defects. These are one of the major things you have to look out for under this confidence of fill results in any project that you are doing. Then some yellow, this indicates difficulty in filling with very possible defects, while the red color indication indicates not filling with heavy defects. Now let's move to the quality prediction. Under the quality prediction, we also have color indicators. You can see from the images there that the quality prediction is standing at 87. It could still go higher, based on modifications that can be made that will not alter existing equilibrium. All right, so the all green is high quality, some yellow is quality issues, while the red color is a clear indication of defective part outcomes, okay, with imbalances. Now let's talk about the pressure drop. These are the active summary of what to look out for under the pressure drop. Now you can increase or rather obtain the maximum injection pressure to improve the confidence of fill from this pressure drop, okay, pressure drop indicators. Now moving the polymer injection locations closer to the problem area or add additional injection points to improve the likelihood of all sections of a part filling. These are things that you can look out for and decide on based on the results of the pressure drop. Now thirdly, alter the part geometry. Complex and thin geometry can cause filling difficulties that require high injection pressure to complete the filling. Then again, you can also select a different material with higher melt flow rate so that less injection pressure is carried to fill the part. Then also you can increase the melt temperature to reduce viscosity of the melt and enable the melt to flow into the mold more easily.
Audio Jungle.
All right, so let's now advance to the temperature at flow front. Now, these are the active summaries you need to take note of as far as this section of the results analysis is concerned. Result as an alternative way of examining the flow distribution, cold spots indicating hesitation. All right, that is what this temperature at flow front does. One of the major things it does that you should look out for. And secondly, you should also look at the areas where the average temperature is too high, or material degradation and surface defects might or may occur. Now let's move on to the average temperature. The applications and very important things you can look out for includes, but not limited to, this could actually be an alternative way of examining the flow distribution under this particular results section, the method. Then the average temperature results should be examined in conjunction with the frozen layer fraction at the end of field results. Let's now move to the time to reach injection temperature results. Now under these are some of the basic things that you need to look out for. Firstly, you need to ask yourself certain questions. Is the part sufficiently frozen at the end of the packing and cycle time? 2. Is the gate freezing off too early before cavity can be adequately packed out? Then 3. Are there thinner regions freezing off before more extreme thicker regions, thus preventing the thicker regions from being adequately filled? Okay, these are 3 major things, and there could be more that you can actually get, but these are some of the 3 major things you should be looking at for as far as the time to reach injection temperature result is concerned. Now let's talk about the air traps. Now the applications and the things to look out for under these include, but not limited to, burning marks caused by air in an air trap, which ignites under pressure and burns the plastic. You might not want this to happen. So air trap result is a very good quality indicator for that. Then secondly, you have the short shots caused by incomplete filling of the part. The short shot that I mentioned it severally in this video, so I believe everybody should know the meaning of short shot. All right, now if an air trap is not vented and is not compressed quickly enough to cause a burn mark, it may cause a short shot or leave bubbles of air or gas in the plastic parts. All right, then the other ones are the surface blemishes caused by air traps. So these 3 things are actually could be really directed towards, giving clean cut indicators of production time and final product. Then the other things that you can see from the air traps include using flow leaders or deflectors, increasing the injection speed to eliminate air traps caused by converging flow front and hesitation. All right, then decrease the injection speed to reduce air traps caused by poor venting and to prevent burn masks. Now we also have here decreasing the part wall thickness ratio to reduce race tracking. Then moving the injection locations so that the air traps form in areas that are easy to vent, such as the parting plane. Now let's move on to the weld lines, the applications and things to look out for. The weld lines can be moved by changing the fill pattern to make the flow front meet at a different place. So in order to move weld lines, you can alter the gate locations and also change the thickness of the parts. Now still under the weld lines, you can improve the quality of weld lines by increasing the melt temperature, injection speed, packing pressure. This will enable the flow front to weld to each other effectively. All right, then increasing the diameters of the gates and runners to make it easier to pack the parts. Now moving injection locations to make weld lines form closer to the gate. The weld line is then created with a higher flow front temperature and is packed with more pressure. Still under the weld lines, applications and things to look out for. Move the injection locations to make flow fronts move more obliquely, turning weld line into a melt line. Place vents in the area of the weld line, which remove air traps, which could further weaken the weld line. Then optimize the design of the runner system. Reduce runner dimensions and maintain the same flow rate. shear heating can then be utilized to increase the melt temperature at the flow front. We're still on the weld lines, application and things to look out for. The weld lines result helps you identify the following problems. 1. Structural problems. The part may be more likely to fracture or to deform at the weld line, especially if the weld line is of low quality. This weakness is a more serious problem in areas of the part that are subject to stress. Now, the other part that these weld lines could actually help to fix is visual defects. A weld line can cause a line, notch, or color change on the surface of the part. If the weld line is positioned on a non-critical part surface, such as the bottom, this may not be a problem. Now, let's move on to injection pressure results. Pressure at end of field results. Now, applications and things to look out for under this result include, but not limited to, during packing, pressure variations affect the volumetric shrinkage. The pressure variation in the cavity should be optimized during packaging stage. Then, the injection pressure result is used with pressure drop result to locate areas where the actual injection pressure is too high. Now, we should also take note of this too, that during packing, pressure variations affect the volumetric shrinkage. The pressure variation in the cavity should also be minimized during the packaging stage. Then the injection pressure results is used with the pressure drop result to locate areas where the actual injection pressure is too high. This is under the injection pressure results. Now, you could also do this is still under the injection pressure result, the pressure at the end of field. You can actually alter the injection location or use additional injection locations to fill a problem area. The number of gate locations depends on part geometry, material, and processing conditions, respectively. And another thing to note there is position gates to create balanced filling pattern and uniform pressure distribution. Now, avoid placing gates close to thin areas that will cause hesitation in areas that will fill early and overpack. Then finally, you can also alter the part geometry. Now, still on the injection pressure results, pressure at end of field results, the applications and things to look out for include hesitation, overpacking caused by high injection pressure, as well as shrinkage. Now, let's take a look at frozen layer fraction at end of field results. Application and things to look out for include, but not limited to, hesitation, overpacking caused by high injection pressure, and shrinkage. Now, growth from results. This is the final part of the advisor result analysis that you should be looking out for, the applications and things to look out for. You have this in your mind. A result that shows an equal distribution of colors will also have a uniform filling pattern and be balanced, like I said in the earlier parts of this video. If the distribution of the colors is not equal, then flow is unbalanced. Flow has to be balanced. This I explained during the real-time video while recording the analysis of the results of this waste paper plastic basket. I did mention that the sequential filling of these parts of the gates of these injection locations was done sequentially. It was not done haphazardly, or maybe 2 or 3 trying to fill at the same time. So this has to be well noted as an indicator, an application for things to look out for as far as the growth from result is concerned. So if the distribution of colors is not equal, then the flow is unbalanced. You should take note of that. And this marks the end of this presentation. I hope you enjoyed it. Please remember to thumbs up this video, and of course share, subscribe,